minutes or so, we give a small break for addressing the participants' question. But you can decide as per your, whatever you think is possible. And then after, say 4:20, around 3:20 and around 4:20. But you can decide as per your right.
Just remind me when
Sure,
okay, 3:30 and this.
Yeah, I will ping you. Yeah, thank you.
Thank you so much, ma'am. Thank you so much, ma'am, for good afternoon, all of you, and let us begin with today's topic, that is convolutional neural networks. And before telling you the nitty-gritty of convolutional neural network, I would like a small background regarding this, which will be helpful for us to understand its importance. So, if we talk about convolutional neural networks, then we need to go back actually.
Recording in progress.
So we need to go back and look in the past few decades when deep learning has proved to be a very powerful tool because of its, of course, its ability to handle large amount of data, and the interest to use the hidden layers has actually surpassed traditional techniques, especially in the pattern recognition. And one of the most popular deep neural network is convolutional neural. So I must mention here that since the 1950s, which were the early days of artificial intelligence, the researchers have struggled to make a system that understand visual data. And later on, this quest has actually resulted in a field that we all know as computer vision. So, so let us take this picture, which will help us to understand different types of tasks which are performed in computer vision. So as you can see here, object detection. Now, like all of us must have heard, those who are working in the field, familiar with this word object recognition. So object recognition is one of the most interesting problem in computer vision, especially after its association with self-driving cars. So now we know that in self-driving cars, we are having many systems which are blended with computer vision so that we can generate a multi-dimensional representation of road as well as all its participants. So also if we talk about object detection, then it can be used in video surveillance, for example, say crowd monitoring to prevent the terrorist attacks, or we may use it in the applications like even finding interest of the customers in the shopping center. So you just spend a few moments on some rack, and maybe next day you will get started getting advertisement for that. Now, to understand this object detection and the complexity, we need to let us start with classification. So when this picture, if you see this, so in this task, what we do is that we are having an image and we want to assign it to one of the many different categories. Categories may be cat, dog, rat, whatever. And so basically what we are doing here, we want to answer the question, what is in the picture? So here, if you can see the picture, there is one cat visible. So means that we are dealing with a single category. Right? So after that, we move to the next level. Now, next level says that not only classify it, but also locate where the object is. So here we want to answer the question, what is it and where is it? So this is object localization. Now, so far so good, like you can see, you have identified the single object. But when we go to the real life scenario, then we are not interested in locating just one object, right? We are interested in locating or identifying multiple objects in a picture. And so even if you take the most interesting example of the self-driving cars, then we need to find out not only the location of other cars, traffic lights, you can say humans, signals, but also we are supposed to take we need to take our decision based on what we have identified. For example, let us say on the road, whether it is a child or there is a paper bag. Right? So here we have shown an example of object detection. So you can see that various objects are being detected here. So here we are interested in finding out all the objects in the image. And then you can see these bounding boxes. So all the objects, then drawing the bounding boxes around. Now, after this, there may be certain situations when we want the exact boundaries. Here you can see these exact boundaries of the objects, which is called instance segmentation. So here, when we talk about, when we say CNN, then CNN is a class of deep neural network which is most commonly applied to analyze this visual imagery, right? So now what happened here, you must have seen such a picture. I will tell you what is this picture about. So again, I will take you to the year 2012 when CV computer vision took a quantum leap, when a group of researchers from the University of Toronto, they developed an AI model that surpassed the best image recognition algorithms at that time, and that too by a big margin. So this AI system, which became popular as AlexNet, this was given name after its main creator, Alex Krzyzewski, and they won the 2012 ImageNet computer vision contest. I will tell you about this contest later in this talk, with the classification accuracy of 85%. Now, you must be wondering that now you are getting it in the 90s. So what is this 85? But at that time, the existing algorithm, so if you, the runner-up, they scored, you can say, modest accuracy, that is 74% on the testing. So if we talk about, if we see this AlexNet, about which we will discuss again after learning the nitty-gritty of CNN. So at the heart of the AlexNet, it was seen convolutional neural network, which is a special type of neural network that roughly imitates human vision. So, and over the, so this is the first venture, you can say, but over the years, convolutional neural networks became a very important part of many computer vision applications, right? So, with this background, let us look at the working of the scene. So now here our goal is to learn useful higher level features from images. So what deep learning does, it learns high hierarchical representations. Here you can see rich hierarchical representation, or you can say features automatically by extracting features at the different levels. So you can see here right from the pixels to classification. What is happening here? DL provides you, or deep learning provides you a flexible, learnable network. And each layer, as you can see here, this is your input data. Now you're starting from these pixels to move up. So each layer of the hierarchy extracts features from output of the previous layer. For example, you can see that here from the pixels, this first layer learns edges, second layer gives you features of the object part, here third layer gives you object. So that is what we can say, that from low level features to high level features. And that is what we mean by learning a hierarchy. So it is learning all those features, high, low level, mid level, high level, starting from the pixel, and ultimately gives you classification. So these layers are, not exactly, but you can say nearly same structure. And remember that these layers are trained jointly. It is not like one by, so in team, right? They are trained jointly. So with this, now I think because you are already gone through the code, so now you are familiar with this neural network. So where we are having input layer, we are having these hidden layers. This is a simple where I have shown only one hidden layer, then the output layer, which is your decision layer. Now here, when we are those neural network which you have studied, now we will talk about them with reference to image data. So when we are saying image data, so let us suppose your input vector is an image data set. Now here you can see the pictures. So pictures like the birds are there. So let us say your target is that you want to classify if the picture contains a bird, right, or not, or you want to see that what is the content of the picture. So if we say that, let us say your picture is of size 256 cross 256, right? So these many pixels. Now 256 cross 256 means how many pixels are there? Double six, 5, 3, 6. Now, so now do we know what is the size of the input layer? Now you know, as I showed you in the previous slide, all these pixels in the picture, they are passed right to your input layer. So it starts from pixel level. So what will be the size of your input layer? This will be the size, right? Now here, let us say how many weight parameters we need if our hidden layer contains 1024 units. So because let us keep things simple at this point of time. So we are saying, okay, this hidden layer is there and it contains this 1024 units, right? So how many weights we need? This multiplied by 1024, right? And what it comes out, it's a long number. We'll say 68132,864, right? A long number there. But so this layer is going to learn these very parameters. Now, so let us see, take this image data and see what is happening. So this, these are some numbers as you can see, but these are actually the pixel values of a block of an image. Now, what helps us? Because we need to analyze this image data for finding out that we are going for classification, basically, or we are analyzing it, we are finding out some patterns there, right? So this image data is now on the one end, this image data is a very high dimensional data. We just saw that, right? But it has redundancies, right? So remember here, you can see these redundancies here, and also it is having certain patterns. So what is our task? That we want to develop techniques so that we may take care of these redundancies and using these redundancies, we can take care of this high dimensionality, we can deal with the issue of dimensionality, and then we can identify patterns. So here, CNN, it is, this network you must have seen in your previous lectures also. So here you can see input layer, hidden layers, and all. I think you can see here they are fully connected, right? And then you are going to get reach the output. But when we go for CNN, we say that it is a smaller network. Now, how it is a smaller network? So now when we go from this large network to CNN, that is a smaller network, there are a couple of questions to be answered. Because as I told you that we need to think over what can we do for analyzing, for taking care of this high dimensional image data in an easy way. So first thing comes when we saw this network, then we want to know that whether we need all these edges as it is being shown in the fully connected model. And also another question that because at every layer, right, weights are there. So is it possible to share some weights? Right. So if we can do this, then if we can get answer of this question, then we can have our network a smaller one. Right? So there we get the answer, and where it says that convolutional neural networks are just neural networks with 3D activations and weight share. So that is what we need to understand, how they are neural network with 3D activations and weight sharing. So we can say that CNN is a multi-layer neural network, which is having like two important things are there. One thing is local connectivity. We will see that neurons in a layer are only connected to a small region of that of the layer before, not all, right? Again, I am repeating it so that you may understand these 2 points easily. So here local connectivity means that your neurons in a layer are only connected to a small region of the layer, previous layer, right? And then sharing, this is another important point. So sharing weight parameters across the spatial positions. It means that basically we are learning shift invariant filter curve. Right? So now with this, let us go to our again our image part and see what is to be done. So when we are saying we are finding out patterns in the image, so you just saw that those patterns are can be very small as compared to your image size. So here the example is taken, that is of eye detector filter in the image. So if you can see this picture, and then here we are talking about eye detector. So we want wherever this eye pattern is present in the picture, we may be able to locate it. So here, what happens in place of, because that we said that this whether we need all those weight parameters or all that large networks. So here, this a small pattern detector can be used in place of the entire weight parameter. So that is not. Now, when you are learning this small pattern detector, then what happens there? This same pattern can be present at different position in the picture. For example, here you can see the eyes. It means that once you have learned that pattern, so that same pattern detector can be moved around, right, in the picture, and then it may detect wherever that pattern is available in the picture. So here in this case, this pattern is an eye detector, so it is going to detect eyes wherever it is present, right, at different locations in the picture. So now here we come to convolutional neural networks, which are allowing us, as I told you, local connectivity and sharing weight parameters. So here they use parameter sharing. And here what happens, I showed you an example of this eye detector, so a small pattern detector that we are calling here as filters, right? So we need to learn these filters and for a pattern, and then these filters are used to convolve over the entire image, right? And how we are learning these filters, how we are getting filters corresponding to a particular pattern. So let me tell you that these filters are learned in the same way as you just gone through the neural networks. So like whatever process is there in the neural network training, in the same way, like we have studied these fully connected networks, the same process is being followed here, and these filters are being learned. So here, there in the, you are having like you are having this hidden layers, right? In the fully connected, here we are having convolutional layers. So in CNN, convolutional neural network, we make use of fully connected layers, right? And here, because the image data, like it's a large size data, so pooling layers are introduced. So we will learn now what are all is about. So before we begin, let us understand this convolution process or operation. So here you can see that this is your picture. Now this is your image. Let us say this is your filter, right? So convolution filter. Now what is happening? Remember here, I must tell you. So there are when we go for this filtering, so there are cross correlation and convolution. So cross correlation is simple sum of product. And when we go for convolution, that is also a sum of product. But what happens? We rotate the filter 180 degree and then perform the sum of product. But for simplicity, what we can do is that we can keep the filter 180 degree rotated, and so that we can simply perform this cross correlation process. That is your sum of product. So don't get confused here about this. We keep a filter and rotated version of it, so that you can simply perform sum of product. Now here what happens, so if you just see here, this is your 3x3 filter. So what we'll do, we are going to slide this filter over this entire picture, so that every pixel, right, we want to put this center pixel, right, so that the pixels in the picture, they coincide with the center of the filter. Now, so what is the, when you are going to go here, because in the picture, so this top left corner, that is the starting point. So when you are placing this filter here, so the first pixel, which is having this filter center here, that is this pixel which is having intensity value 6. Now what we do, we simply do this multiplication of the corresponding term and then do the addition. So here I will tell you these things in more details also. So, but here you can see this 3 into minus 1, 0 into 0, 1 into 1, then 2 into minus 2, 6 into 0, 2 into 2, this 2 into minus 1, 4 into 0, and then this 1 into 1. Now add them. and so it will produce one real number, right? So that real number, where we are going to write it? At the position corresponding to this pixel which is having intensity value 6, right? So here when we do this sum of multiplication, we are getting this value, that is -3. Now similarly, what will happen? Now we will again move this filter, so we will slide this filter. Again we will get these 9 multiplication and these additions, and we will get pixel value here, right? So this way we will move one step forward, and then in the next we will move one scan line down, and here we are going to produce this value for pixel number 4, that will give you this, right? So that is how convolution is done. So here what we in CNN, what happens that we are having not only one filter but a number of filters, right? So we will, the convolution layer here has a number of filters which are going to perform the convolution operation. So for example, here you can see that here you can see just one filter which may be eye detector. There may be another filter which may be, let us say, nose detector or mouth detector, whatever, right? So we are having a number of filters. So let us again, if those who have got that from that slide, that is perfect. But here we can take this process in detail so that it will be clear to all of you. So again, let us say this is my picture, small 6x6 picture, and this is my 3x3 filter. So now what, as I told you, what we'll do, the filter is placed here. Just a minute, slide number 10. Okay, don't worry, I am going to explain the working of the slide number 10 only here. So here, just okay. Like here, I just showed you that how when you are putting this 3x3 filter here on the image, right? So a real number is produced, which we are going to put corresponding to the pixel which is having value 6 here. So this is the pixel which is corresponding pixel which is having value 6 here, and you are writing here -3. Now let me repeat the whole thing, how this -3 is achieved. So let me take this example and you will get the same thing. So again, now what is going to happen? We are going to place this filter here, right? So the first pixel where you can place this filter entirely on the picture. So this pixel is there, your center. What is happening here? You can say that, just imagine that this blue window is here on this red box, right? So on the 5 it is 1, on the 1 it is 0, on the 7 it is -1, just they are overlapped, right? Just imagine that you have put this window here, right? Now what we'll do, as I told you, sum of product. So we will take the product of the corresponding terms. So as you can see here, this 5 is multiplied with 1, then this 1, that is what I explained in slide number 10, right? So this 1 is multiplied with 0, this 7 is multiplied with -1, again this 7 is multiplied with 2, this 2 is multiplied with 0, 5 is multiplied with -2, and so on, so right? So we have done this multiplications, right? And then added them, right? So that is sum of them. So we have added them. Now when you are going to do this, it is going to produce a number, that is 2. So where we are going to write, in this example, I mean in here this center pixel value is also 2, and you are getting output, but this will also not be same in all the cases. So what will happen in the output image, this pixel value, right, will be set as 2. Right? Now what will happen? We will move the filter. So see here, when we are going to, so what is happening here, how this is being done, just see here. So we are going to convert the image block and filter to, you can see here these column vectors, because when you are going to implement it, for implementation purpose, so you are converting it into the single column vectors. And then what is this operation? This operation is nothing but the dot product. So when you are, this is your input. So what is your, here you can see these pixel values. So 5, 1, 7. So you have just written it as a multi-vector. Now this is your filter. So 1, 0, -1. Then this 1, 0. Okay. This will become 2 0 minus 2, so right? So then 1 0 minus 1. So that I will correct it in the when I will give the slide. So what is happening here again? So we are going to multiply it, right? So that is how we can say that dot product, and this is produce one number. See, let me first of all let me come to your question that how we are going to identify it. So here we have got this response, and then what will happen? The filter will be slided, right? So we are going to slide this filter by 1 pixel, right? So earlier it was having these 9 pixels. Now this is having these 9 pixels, right? And again we will perform the same process, right? So here the corresponding, just imagine here that 1 is here, 0 is here, minus 1, then it is your 2, 0, minus 2, then 1, 0, minus 1, right? So here what is happening, we are going to, when we are going to multiply this then and add this, the response is this. So okay, the details will come later, but here let me answer your question. See, these filters are, when we are talking about simple, right, detectors, not in terms of convolutional neural network, then filters are, we decide based on the pattern which we want to identify, right? For example, if you look at this filter, what this filter will give you? When you are using this filter, this is nothing but an edge detector. So this will give you an edge there. So that there is a difference between the, because if you go to the picture, this discontinuity. So if you say here, this is an edge, right? So because earlier here you can see these white pixels, then these blue pixels. So these edges are to be detected. And this simple filter which is being shown here, that is an edge filter. So depending upon the task, like corner filters, these are the simple things which you can do, and you can design your filter depending upon what task you are doing. Now, when we talk about the filters which we are going to use in the convolutional neural network, then there the filters are being learned depending upon the pattern. So the corresponding to the pattern, the filters are being learned there. For simple applications like edge, like this horizontal edge, vertical edge, corners, you can design your filters, right? So here you are, so okay, let's again come back here. So this, you have put it here, and then you got this sum of product. So this is giving you a number minus 17. Now this pixel, right, will be, what value will it will get in the output image? It will get this minus 7, right? Now again we are going to move this filter here, slide this filter. So these 9 pixels are going to participate, and again we are going to do the corresponding terms multiplication and then this addition. This time it is giving me minus 6, right? So this 7 is replaced by minus 6 in the output. Okay, and this way the process will. Okay. Now, if we go for, this was a simple example when you are having one. When we talk about red green, so when we talk about this color image, then we know that every pixel, so when we say 24 bits, so 8 bits are coming from red, 8 bits are green, and 8 bits are blue, and their combination, right, decides what is your color. So when we will go for color image, you can see here red, green, and blue, 3 channels are there. So it means that now we need 3 filter copies, right? So here one copy to work with red channel, one copy to work with green channel, and one copy to work with blue channel. So here you can see that. So this is your image, and this is, so we are having, these are the 3 copies. So you can see that these are the 3 channels, and these are the 3 copies of a filter to process this. So here when we do this convolution on the RGB image, the same operation, but how we need to do? Now we will make 3 copies of the filter, and then we will apply convolutional operation on each channel. Right? So here we will get 3 values, okay? 1 for each channel, and then we are going to add these 3 values to get a single output. Right? So see how. So let us see here. Let us for this picture, right? This is your red channel, this is your green channel, and this is your blue channel. Now let us say this is your filter. Okay, this is your 3 cross 3 filter. Here, like this, I will introduce you later. So this is your 3 cross 3 filter. Now you are placing this 3 cross 3 filter, let us say, at the corner. Right? So when you are going to do this multiplication and addition, as I told you will get the response here for this pixel, right? That is your 2. Okay, response again for this pixel, that is your 1. And when you are going to do this 9 multiplication and additions with this filter, response for this, so we got 3 responses here, each corresponding to each channel. Now we have to get a single output. So here you can see this single output, right? So here, although 2, 1 and 0, it should be 3 here, right? So here you can see this red channel, green channel, blue channel values multiplied by the filter coefficients, right? And then finally we are at. So this is, and apart from this, remember bias. So after doing this, that bias is to be. So now let us see this convolution layer. So here now it means that how we are treating our image now. So my image is 32 cross 32, and because of 3 channel, we are saying 32 cross 32 cross 3 image, right? Now, because my image is now this, here we are, see, what is happening? I was just telling you a way how to do it, right? Then later on, when you will be learning filters, then situation will be, right? Initially, you can understand. So here you can see this, your filter, initially this 5 cross 5 cross 3, so 3 copies of that. And later on, what will happen? The filter will learn. So now we are going to convolve. Yes. So here, what is happening? Remember always that filter must be extended to the full depth of the input volume. So now we are we will convolve the filter with the image and we will compute dot product as I told. Right? So this will give you, when you are putting, let us say we have put our filter here. So and then this filter, these are the weights. So this will produce this one number, right? So as I told you, how this one number is going to be produced, remember this 5 cross 5 cross 3, right? So that is your 75 dimensional dot product and one bias, right? So that is how your response for one pixel is being generated. So remember that at this pixel location in the input image, there are red, green and blue channels, right? Bias you will be like initially you will pick some value and then later on it is to be learned. So it is same as you have done in the neural network. So this is how you will get a hidden neuron in the next layer, right? By doing these 75 dimensional dot product and adding them. So now here you can write, because as I told you, convolutional layer 3D activation. So how this term 3D comes, this 3D terms comes because of here, because your image is having those 3 channels. So here when you are doing this, this is your output, the neuron in the next layer, and what we'll say here, this is the sum over the 3 axes. So you are going to perform this sum of product for each different channel, right? And then you are adding the response. That is your 3D. Now, similarly, what will happen? We will produce, as I told you that here in the convolutional neural network, you will get in a convolutional layer, you will get not only one but multiple filters, right? So let us say here we are having another filter, right? So we are getting corresponding to the same like position here, you are getting 2 neurons, right? So this is corresponding to the first filter, and this is corresponding to the second filter. Right. So the second filter, again, the process is simple. I mean, process is same. You are going to do this sum of product for each channel and then add the response, right? So similarly, we may have a number of filters. Now, so this is what I mean is the first filter and the second, right? So these are the weights and this is the bias. So every filter is having its own phase weights and mass. So here, like you can see that we can grow in the depth. So for example, here when we are using 5 filters, so you can see that this neuron is generated because of first filter, second filter, third filter, fourth and fifth filters. This is how you can adding on. You can add on more output. Right? So here you can see that this will form a column in the output volume. That is your, you can say that this depth, depending upon how many filters you are using. So each neuron, remember that each neuron here is generated with its own 3D filter and own scalar or its own bias. So here, what is happening? So this process I showed you just for one, when you are placing your filter on one area in the image. Now, what I told you in the convolution, what will happen? You are going to place it right from here, right top left, and then you are sliding it across the row, and then come down to a column. Again, you are going to slide it like that, right? So when you will do this, was the result for just one neighborhood. Right? So let us say if your filter is 3 cross 3, so this output is basically result of those 3 cross 3, 9 pixels. But we need to slide it over the entire picture, and that is how we will generate the full volume. Right? So by repeating this, we are here we are having this these set of weights, or you can say that these filters, right? So each filter will add to one layer in the output one. So here we can say how this weight sharing is coming. We can see that each filter shares the same weights, but remember that each depth index has its own set of weights. Right? Here you can see that this filter will have some other weights as compared to this, right? So these filters, they are having different weights, right? Different set of weights. But here, if we talk about each filter, when you are convolving it here, moving it here, then it is sharing the same weights. So I will give you some examples also. So here, this is just one example, and more I will give you towards end. So here, this is your one example of the weight sharing. So here you can see this is your picture data. So you have arranged it in a 1D, as I showed you in the previous slide. So you have arranged it in a 1D, and then this is going to give you one response. So you are going to multiply it corresponding to your, let us say here, this 3 cross 3 filters. So we know that you are going to place your filter here, and that is how you can see these 3, 4, 7, 9, 10, 12, and this 11, 15, 14, and 15 are participating. Right? Now, when you will move it here, then what will happen? Now this 4, 7, 8, and these 9 pixels will participate. So this same, whether you are talking about these 9 pixels or you are talking about these 9 pixels, these weights are same. Right? So that is what is there. So we may think this convolutional layer as a hidden layer in which various inputs, here you can see this various inputs, right? They are sharing the single weight parameter. Right? So here you can see that this 3, and then later on when you are moving it 4, then this 7, they will be having the same parameter, sharing the same weight parameter. Now, so with weight sharing, when we are going for, it is called basically convolution, right? So now, if you do not go for weight sharing, so then it is a locally connected. Now here again, so get it in that, as I told you that we are using filters, and each filter is going to add one layer in the output. So here you can see that this is the output of one filter, right? Now, so we can say that one set of weights, right? That filter, which is nothing but we'll say that set of weights, that gives you one slice here. Now here, let us say we want to get this 3D output of depth D. It means that we need to use D different filters, right? And as I told you that when we talk about convolutional networks, convnets, CNN, so they use many filters, right? Not 64, 102, large number. So here we can see that when we talk about the this layer, and so here there are four things. This what is the output depth, right? What is your input depth? What is the size of your kernel or filter, basically, right? So what is the size of the filter, size of the input, and then this is your output. Basically, how many filters you are using. See, it depends, like because these layers you are using, so that you need those parameters are supposed to be tuned. So we'll come on it later, right? How it is learning. Right now, I'm telling you basically. Definitely, it will depend. That is how you are having the different arguments. So now when we go for, here we need to understand two terms. One is your feature maps, another is your activation map. So when we are talking about filters, then let us say we are using two filters, then your output will contain two channels, right? And these are called feature maps. So we'll say that one for each filter. Now here you can see that another example. So here you can see this is your input image, red, blue and green channels. Now this is your filter number 1, this is your filter number 2. So filter number 1 here, that is giving you again this one map, right? So this is nothing but a feature map, right? So when you are doing this convolution process, right, and then you are going to get this feature map, right? So these weights and plus this spice. So here this second filter, this is again giving you a feature. Okay. Now, what is activation maps, right? Because activation word you must have seen in some of the slides. So what happens once we get, because convolution, that is a linear operation. If you just saw this convolution, I told you, this is nothing but the, as I showed you, this dot product. So that is nothing but the element-wise matrix multiplication and addition, right? So just a minute. So this active now we need to introduce some non-linearity here, because what is the purpose of introducing non-linearity here? Because most of the real world data we want our convolutional network to learn, that would be non-linear, not the linear. Okay. So because of this, the activation function is applied on all the entries of each feature map to get the activation maps, right? So how this is being done? Let us see here. So this is the in the previous example. So let us say you got this feature map, right? So feature map, simple result of this convolution, right? So just do the convolution, add the response for the 3 channels and got this. So you got different feature maps. Now you are introducing this non-linear operation. So let us say here, this activation function is your ReLU, right? ReLU is rectified linear unit, this activation function. So what is happening here? You are applying now here. This is, so you are, whatever is the output of the feature map, here you are applying this ReLU activation function. For example, here I have taken this ReLU. So here you can see this feature map, weights and then bias, and then you are applying this, and that is your output. This is nothing but your activation map. So here you can see this ReLU is actually an element-wise operation which is applied per pixel, right? And what it does, you can see here, all negate. So this is input output. So what is happening here? All negative pixel values, because you don't know what weights are there. So it may happen you are going to do this multiplication and addition, you may get some negative values also. Right? If you remember, I showed you also in one of the examples. So here all these negative values will be replaced by 0 and then right, it's the feature map. So that is what is the one example here of this activation, right? So this is your feature map, and when you are applying your activation function, which is ReLU here, then this is your activation, right? So rectified feature map, basically this is your activation, right? And as you can see, this ReLU function, what it does, the max of 0 or E. So if input is negative, then it gives you 0. Otherwise, it is, you can see this. I hope this is clear up to this point. Please let me know if you need a break here.
Yeah, Priti, thank you so very much. Let us have a small break with some questions. Some people would be asking such a wonderful explanation. Participants, if you have any questions, please raise your hands so that we can unmute you. Any questions, participants? Yeah, Amit, just a minute. Give me a minute. Yeah, you please unmute yourself.
Yeah, ma'am, my question is when we use filter 3x3 filter, suppose, so we are getting the number on the center one. So what will happen to the first corner pixel?
Yes, I will come to that. So what is happening here? So when you are starting with the filter of 3x3, basically if you're putting it on the leftmost corner, so this 1 pixels on the left and 1 pixels on the top, they are not going to participate in it. And that is what you can see here also, which I was explaining with the next right here. So when you are applying this filter here your filter is 5x5 filter. So now 2 pixels left and 2 pixels top. Similarly, 2 pixels bottom and 2 pixels right, they are not going to participate. And that is why size of the output is going to be decreased.
And
Thank you.
Second question I had, ma'am.
Yeah, you have another question, Amit? Yeah,
Yes,
please
ma'am.
continue.
So what is the driving factor to decide on the size of the filter, ma'am?
So basically, what is the object you want to learn with that? Because we are learning the small patterns, that is why 3x3, 5x5, we do not take very large size filter. We take instead of, especially in the convolutional neural network, like if you take example of VGG, instead of taking those large size filter, they took small size filters and they increased the number of.
And also you here, I can see the depth of the filter, like 5x5 into 3 matrix. 3 is RGB. That's what I can understand. 3 layers, right, ma'am? So why we are using 6 in second layer?
That is what I told you, that in the convolutional layer, actually this slide I haven't explained you yet. So basically when we say convolutional layer, as I told you, it is having many filters. So let us say this layer is having 6 filters, right? And this layer is having 10 filters.
Okay, thank you. Let me give chance to Madam Satya Devi. Please unmute yourself. I think I have unmuted you. Satya Devi?
Yeah, ma'am. Good afternoon, ma'am.
Good afternoon.
Ma'am, you're adding bias, no? So, depending upon the image patch, that means 3x3 filter means when I have to convolve with 3x3 image patch. So, for each 3x3 image patch, regarding the, based on the filter size, I have to add 1 bias. Or how many bias I have to add it?
For each
or else for each
filter,
pattern wise, I have to add a bias.
Pardon?
So, actually,
each filter will have its own bias.
Okay, each filter means 1 filter for 1 bias, the whole image. Say for example,
you see what are you doing here? As you must have done in the neural network also, you are multiplying it with weights, then adding the bias. So no matter if your filter is 3x3, 5x5, 7x7, it bias is not like if 3x3 is there, then 1 bias, 5x5, then 2 bias. It is not like that. Whatever is the size, whatever may be your filter, there is corresponding to those weights. That filter there is.
So based on the depth, I can add it.
Yeah, so that is what I'm saying. Depth is depending upon how many filters you are using, and each filter is having a bias.
Yeah. Okay, ma'am. Okay. Yeah, thank you, ma'am. Thank you.
So there is one question. I'm saying this 225 cross 225. So as I told you, this will be your, because you are starting with your input will be all these pixels. So this 225 cross 225 is your input.
So Neha Rathore, please unmute yourself.
Good afternoon, ma'am. Ma'am, actually you asked why we are adding this non-linearity. What happens if we do not add non-linearity in the network?
Yes, this
Does
is
it
very
make
important.
any changes the output?
See, the problem is the nature of the data in the real life. So if you consider real life data, it is not we say most of the time it is not linear in the nature. So why we are doing this all exercise? We are developing this CNN so that it will learn the patterns from the data. And this data is non-linear. So we need to introduce some non-linearity here. And that is why these activation maps are introduced. Because as I told you, this convolution operation, that is a linear operation, sum of product. Right? So because we are dealing with a data which is having non-linearity in it. Right? So to deal with that, this non-linearity is to be added. So that is how these activation functions are introduced. And that is how we are not only stopping at the filter maps, but we are going for activation maps. We continue.
Thank you, Priti. Another question by Smita Bal. Please, Smita ji, you unmute yourself.
Very good afternoon, ma'am. Ma'am, my question is why we are adding a bias to the neural network?
Why we are adding bias to the neural networks? I will request Professor Oja to answer this question.
No, so you can answer better, but because you have given me a chance, so I would like to speak here. Somebody actually asked in the previous class also of Professor Roy. So what happens bias? Think about it as neuron is what we are all having in our brains, these neurons, right? Everybody is unique in terms of thinking. He may be having bias about, say, I may be having bias for white color. You may be having bias for green color. So in spite of everybody having the same method of processing information, the information processed by each person, each individual person is differently processed, right? So why it is processed differently? Because they have some biases towards the surroundings. I may like nature, you may like high-rise building. So one doesn't know. So that is what I'm telling you. The mathematical thing is that we will be making it an affine map in terms of instead of making a linear map, I'm making it an affine map by adding a bias W1x1 plus W2x2 plus W3x3 plus B1 makes it an affine map from the input domain to output domain instead of a linear map. But the idea is, let us look at from the cognitive side also, that every single information processing unit in our body, that is a neuron, has a bias of its own type. So it's not simply the y-intercept on this line, which is the range line, but it is to give a freedom to each neuron to act independently. That is the reason biases are added, right? And secondly, as I told you, that if you want to treat it as a mathematical element, then instead of a linear map, we are making it an affine map. And affine maps are ratio preserving, they are scale invariant, they are rotation invariant, they are shear invariant, all these. So invariance by making this transformation is preserved. Invariance in the data characteristics is preserved, right? I hope, Preeti, I have answered the question.
Because I thought they must be doing it earlier, so they must be having some.
Yeah, so because Parthapratim Roy also, somebody was asking. Thank you. And there is another question. I hope I have made my point clear.
Yes, ma'am. Yes, ma'am.
Thank you.
Ma'am, another question. Now, what is the difference between valid padding and zero padding?
I'm not getting your question, please.
Ma'am, what is padding? in CNN we are adding a padding method to increase the to reduce the dimension. So what is that padding? That means zero padding and valid padding.
Padding you're talking about. I think she will, madams will come. Madam will be talking about this perhaps, yeah.
I think she is talking about pooling, so we'll come on that. So I think let me start again.
One last question by Sumati. I request you to please unmute yourself.
Good evening, ma'am. Ma'am, how the 32 cross 32 cross 3 will be reduced to 28 cross 28 cross 6? And again, it will be further, it is reduced in the subsequence.
Let me explain.
Right? Whether there is any formulas, ma'am, any mathematical?
Let first
we are going to cover this, right?
Yeah. And then we will come to formula also.
Yeah. Okay, thank you. Perhaps she is going to cover. Thank you. Thank you, Sumati ji. And yes, Priti, if you want to take a small break, you can take. Otherwise, we can
No, I think otherwise we will not be able to cover.
Sure. You please continue. Thank you so much.
As you, I think Sumati, I think she has asked the last question. So have you seen here? Just a minute. Have you? Okay. Yeah. Okay. So have you seen here when I was having this picture and I am placing my 3 cross 3 filter here, then what happens that the first value I am producing corresponding to this pixel, right? It means that because when I will place my filter here as a keeping center this pixel, then my filter is going out of it, right? So it means that this top column and this left column is not participating. Right. Similarly, here what happens when you are taking this 5 cross 5 filter, then what will happen when you will take 5 cross 5? See, the first pixel where you are able to place center here, that is this. Right, this is right. It means that 2 columns here on the left and 2 columns on the top, they are not participating. And that is why what is happening when you are doing this convolution here, 32 cross 32 image and your 5 cross 5 filter, the output volume is 28 cross 20. Right? One thing is this. Then what happens here? Again, you are using this. So now your output of this layer is 28 cross 28. Right? Now, again, you are using a 5 cross 5 filter. So again, what will happen? There is a reduction in 4, right? So here you can see, because what happens here, as I told you, 2 left columns, similarly 2 right columns, right? So that is how the reduction in 4, so 32 to 28. Now again, there will be a reduction of 4. So we are going to get from 28 to 24, right? So that is how the size is reducing, right? So now the question comes, how is this process not clear to anyone? It is giving a message that 2 people have raised hands. So if you have any question, please drop it on chat. I'm looking at that. I'm constantly keeping a track on chat. So please drop. So I hope this process is clear. So what is happening? That is how the size is decreasing. Now here I wanted to show you one thing. If we talk about CNN now, so we are having a sequence of convolutional layers, right? Interspersed with activation functions. So activation functions, for example, this here you can see that ReLU. Okay. No, not the. So how? See here, what is happening? Why this is increasing? Because now your output is 28 cross 28 into 6. Because see here, what I told you, whatever is your input volume, you need to take with that, right? So here it was 32 cross 32 cross 3. So you have taken 5 cross 5 cross 3. Now here, because there are 6 filters, so here what is the depth? 6 is the depth, right? So now your input is here 28 cross 28 into 6. So now you will use a filter that is 5 cross 5 cross 6, right? So, and then there are, now here the depth is 10. So now the output is 10. So image size is, because of this 5 cross 5, your image size is 24 cross 24 and this depth is coming with this number of filters. I hope now it is clear. Yes, I'm coming on that. This definitely, this reduced size will cause loss of information. But I hope this thing is clear. So we did filter map, then we applied this ReLU activation function, and that is how we output. So now here you see this is another, this is one example. We will come on back propagation also if you allow me to reach up to that point. So we can, here you can see that this 3D cube, right? So those filters, here you can see that 32 filters, right? So here these are the 32 filters, and each filter is, you can say, this 5 cross 5 cross this. So here you can see how the filters look. So one filter, you can see here will give you one depth slice, yeah, or you can say one activation. So these are, you can see that 32 filters. Now what happens? This is your filter number 1. So filter number 1 will give you slice number 1, right? Now you will, let us say this is your 5th one. So this is, again, you can see that every filter will generate a slice. That is how you are getting output. And that is what I showed you previously. So when you have used 5 cross 5 cross 6, right, then your depth of the output volume is 6. Now in the next layer, what you did, you used 10 filters. So the depth of output is 10 there. So here like 32, so you'll see that the 32, the depth will be 32, right? So 32 responses will be there, 32 activation maps will be there. So here, this is one example we have taken from our lab. So this image and vision engineering lab we are having, where we are working on several problems. So this is one of the, as Madam told you, that we are working on the ophthalmological diseases also. So you can see that this is your fundus image with cataract in the left eye, and this actually we have got with a data set where the data of patients both eyes is being released again under a competition. So these are the activation maps, right? So first convolution layer activation map, second, fourth, like that. So you can see that the level of abstraction is increasing at the high level. So remember, when I told you in the beginning slide, like hierarchy. So first edges, then some parts of the object, then finally these objects are being detected. So these are the two examples of the activation. So today you will do in the lab, and then you will see how the activation maps are generated. This is another fundus image with the glaucoma eye disease, right? So that is how you can see the activation maps are being generated. So as I told you that one filter will give you one depth slice, right? Now, but if you look at these 32 filters here, then you must be able to observe that some filter detect almost same patterns. Right, so here these activation, you can see that some, right here, right, the same sort of patterns. So it means that the number of filters can be extra, and that can lead to a redundant information. But at the same time, if we will use a small number of filters, then what happens? We may lose, we may get a loss of pattern information, right? So that is why it is better to use a large number of filters in the beginning, so that we to avoid any information loss, right? So that is what is the concept. Now again, so let me revise you, because so many there should not be any confusion. So let us say this is your image 32 cross 32 cross 3, filter 5 cross 5 cross 3. So what is happening? You are going to convolve this filter over all spatial location to get your feature map, right? And then you are applying activation function, and that is how you are getting this activation. Right? So one set of weights will give you one size. So that is what. So now you have repeated it for another filter, so you get another activation map. Here size is 32 cross 32, so 28, right? Like that. So that is how you can see these 6 filters are there. So that is how you are getting 6 activations. Right? So that is what is the size. Now here you can see that how you are going to choose the number of filters, because many of you were asking such questions. So number of filters you are going to choose when you will create your CNN maybe today in the lab, and that depends. Nobody can give you some magic number that this should be there, right? This will depend upon your application and your data input type. So sometime with when you will learn the concept, then you are going to learn how you need to, or how many filters are good. So typically when we say that, as I told you, that we don't want to lose any pattern, so a sizable number of filters are chosen, right? So that we can extract maximum features. So now the question comes that what are you learning here? That is a very important question, and must have answer to it. So what we are learning here, you see the filters. So like in the first convolutional layer, you have used 6 filters, next 10 filters, and I mean that is how. So what we are learning at the end of the process, we are actually learning the filters. So in the nobody knows like what is the when you are using it for a classification of certain data, nobody knows what should be the filter coefficients, right? What should be the weights of the filter. Actually, your convolutional neural network during training process learns the filter. So what happens initially, you just initialize those filters randomly, right? You are not setting it with some particular, like some random initialization is there. And gradually what will happen with the training data, the filter coefficients, they will be updated. And then finally you will learn the filter. You will say that now my CNN is has been generalized and it will be able to identify several different patterns depending on your training. So you can see some demo here for ease of understanding. Now here comes this process, because what happens here, if you see this input and so the output volume, so definitely someone has written also that we will lose information if output volume is decreased, definitely. So what happens here, if you just see, this is your 3x3 filter, right? And this is your 8x8 image, but your output is 6x6. So what is happening? Because when you are placing your filter here, the first value is generated for this, right? So that is how you can see the size is reduced. So now when you are moving it, so what happens? How you are moving it? We are moving it 1 pixel right. Now when you are moving it 1 pixel right, now it is generating value for this pixel, right? That is this. Now again you are moving, you are getting this value. Now this is value. Now what is happening? Now there is last this thing. And when you are moving this, you are getting. So you get all, what is happening? You get all pixel, this output. You get these values, right? So these values are, this was your first one, second, third, fourth, fifth, and sixth. So first, second, third, fourth, fifth, and sixth, right? Now when you will place your filter, you will move 1 pixel right, then your filter will go out of the image. So what will happen? What is happening here? So now again, you know that this sum of product and plus this bias, that is. So here, that is, so what, how many pixels we have moved? We have moved it 1 pixel forward, right? Now, so that is, so my stride was 1. Now let us say, we can also convolve by another stride, that is, let us say stride is 2. So when I am moving this 1 pixel forward or this thing, then the size is reduced like you just saw in the previous 8x8 to 6x6. Now again my image is 8x8, but now my stride is 2. So what is happening? My next pixel is this. So it means that I have generated value for this one. Now it is shifted like this. So this one, then this one. And after this my filter go out. So when I am taking stride 2, then what is the size of my output? It is 3x. Okay. So we can see that with certain strides, we are not able to cover all input, right? And here you can see in this particular example, the output becomes half of the size of the input. Okay. So here now, so we will take the issue of image dimension. So here you can see this activation map 32x32 to 28x28. So now what happens? So this operation with the filters, as I told you, that reduces output volume, and the filter values are initially chosen randomly, and gradually these filter values are updated, and at the end we will say that this filter has learned to detect a small pattern. So let us say we talk about output volume. So your picture is this 256 cross 256 into 3. And let us say we are using 8 filters, each of size 5x5. What will be the output volume? So can you answer? Okay, just see whether you are able to understand or not. Now, remember that first of all, your filter will be converted into 5x5x3. Right? Then we are going to do the convolution. So that is how, what will happen? Because this is a 5x5 filter. So what will happen? 2 and 2, right? If your stride is 1. So 4 pixels, right? So here you can see 256 minus 4. So first understand it like this, and then it is easy to put in formula. But if, apart from formula, let us have a informal understanding of this, right? So that you are not dependent on the formula. So what is happening? 5 cross 5 filter. So the 2 size 2 up, 2 down, 2 left, 2 right. So reduction of 4. So from 256 cross 256 to 252 cross 250, right? And because of 8 filters you are using, so in the output volume will be this 252 cross 252 cross 8. I hope this is clear. Now come to this formula. Okay, so you can do whatever I told you. You can do it for different strides. So let us say this output size is this n is the size of the n cross n size of the picture. F cross f is size of your filter, and then you can get your output size by using this simple formula. You can just use this and check with what happens. Simple. Now, so here, now I hope the situation is clear. So when you are using this 6, then it is the output volume is 6. Now here output volume is 10, and so that makes sense. Now here, as you all identified that the size is reducing, right? So further, if we are going to use further, let us say 5 cross 5, then further it will become 20 cross 20, and what will happen? So here there comes a solution. Solution is pad value, right? The form. And let me tell you, there are different sort of padding, mirror, replicate, like, but we will not go into that detail. The most common one, simple one is there, that to do the zero padding. Because if you remember that when we are using 3 cross 3 filter, the problem is of the top row, bottom row, left column and right column. So let us put let us do the zero padding. So we have added the rows and columns here, and the values are set as 0. Now, what is the advantage of it? Now you can see that because your actual image was this, but when you were placing your 3 cross 3 filter, you were getting value for this, right? But now you have padded it so that this pixel is also participating, right? Now you can place your filter here, and this pixel is participating. And then also, what will happen? This again, this size will be reducing, but you have already done the padding. So the dimension reduction will be controlled, right? And so the dimension reduction is controlled, and your corner pixels are having better contribution. So that is what is the general solution, right? So now let us take example of the zero padding. Let us say your input image is of size 7 cross 7, and your filter is 3 cross 3, and your stride is 1. So what will happen? Let us say you have padded your picture with 1 pixel border. So what will happen? The size will retain, because what was happening with 3 cross 3 filter, the size was reducing here with the one this thing, right? So now you have added 1 row, and one row at the top, 1 row at the bottom. Similarly at the column, 1 left column, 1 right column, so that you are able to maintain the size of the picture. And so convolution layers, they mostly use a stride that is 1. And so remember that if I ask you that this is the filter size and what should be the padding you need to do, right? So remember here, padding you need to do, that is this filter size minus 1 by 2. Or in general, you can understand when your filter size is 3 cross 3, right? So you need this padding of 1. Now your filter size is 2 cross 2, because the initially 2 pixel top and 2 left will not be able to participate. So the padding should be, you should pad it with 2, right? 2 rows and 2 columns. So you can do this, or so with this, let us try to understand, let us see what you have understood. So let us say your input volume size is 64 cross 64 into 3, and we are applying 10 filters, each of size 5 cross 5, padding, because see the 5 cross 5 is there. So if you want to maintain the same size, then you need to do the padding, T should be set as 2, and your stride is 1. Now, can you answer these questions, any one of you? If you will try, it will be good. Otherwise, I will tell you. What will be the output volume? I have already told you in fact answer of this question. What will be the size here? See, we need to fill in these three numbers. Anyone, you may drop it on chat also. Okay. No, same is this, right? Because of padding, as I told you this thing. No, not 63. No. See, because of this padding, you have already done this padding, right? With 2. So, yes. So, this size will be this 64 cross 64. This is the size will not reduce here, right? Because you have already done padding. Okay. But, and then you are applying 10 filters. So, what will be the depth? The depth will be. So, this will be your output, right? 64 cross 64 cross 10. Now, second is how many parameters are there in this layer? How many parameters will be there in this layer? See, your filter is 5 cross 5. So, your filter is 5 cross 5. So, 25 parameters, but you have 3 filters, right? So, 5 cross 5 cross 3. And then 1 bias. Right here. So 76 parameters, right? And then how many parameters you are going to, learn. So now you know that this 76 into 10 because 10 filters you are. Okay. So no, this is there, right? I hope you got it, right? So 760. So if you are not able to, you can get all things done with these formulas, right? So if you want to know what should be your volume size, you can do it there, right? So like your image was 64 cross 64. So here you just put it there, what you have there. So 64 minus 5 plus 2 into 2 because padding is 2 and then divided by 1 and then plus 1, right? So you will get the same, right? So you can do it either using formula or by having that understanding. So remember always depth will be the number of filters. So now after convolution, let us see what is the difference it makes, convolution and fully connected layer. So fully connected layer, let us consider our input image of size 32 cross 32, and so we need to flatten it first, as I showed you, convert it 1D vector. So when you will convert it in 1D vector, this will be your size. And now let us say there are 10 neurons in the first hidden layer of your fully connected network. Then we know that each unit will look at the full input vector. So what will happen here? How many training parameters will be there? You can see here 3072, and each will be looking for full input vector, right? So 10 neurons here, and each is looking for a full input vector. So 3072 cross 10. And then 10 filters are there, so 10 bias. So if you just see there, these many training parameters. Right? In this example you are talking about, see, when you will use 10 filters, then definitely out, so that is your output volume, right? Yes, 10 will be the output volume. So here I am taking example of this fully connected layer. So in the fully connected layer, when you are going for this, then these many parameters. Now let us see in case of fully connected layer, if my layer is convolutional layer, right? Then what will happen? If my layer is convolutional layer, then again let us say the same input 32 cross 32 cross 3. Now we are having these filters. So 3 cross 3 cross 3 and 10 filters are there. So how many trainable parameters are there? See this? Tell me, do you get this number? How do you get this 280? See, this each filter, when we talk, see each filter is this. So in each filter, what is this? 3 cross 3 cross 3. 27, right? Plus 1 bias. So 28. For each filter, it is 28 parameters and there are 10 filters. So how many parameters? 2, right? So here, what is happening? Only 280 with the convolution layer. As here you just saw, when we are using the same picture, 32 cross 32, And 10 units here, again 10 layers were there, or you can say 10 neurons are there in the hidden layer, then these many there. Right? So here it comes the understanding. So when you compare this convolution and fully connected layer, so let me take the next slide. So here, just to show you that each neuron looks at the full input. Right? Here. Okay. Now let us see this example so that you will please now have some focus here, so that, because that is the main point of the segment you need to understand. Now, so here you can see this is your filter and this is your 6x6. Right? Now when you are placing your filter here, then your output is 2. Now again do the same. Right? Now what? So how do we do this? Again, your image you have arranged it in a 1D vector, right? So that is how your image in 1D vector, and then it is giving you, when you are using this filter, it is giving you value 3. So here by different colors you can see the, you can do the matching. So here this 1 multiplied by this top element there, this yellow one, this is corresponding to this yellow, green one, so that is how this color matching. So correspondingly multiplication is there and addition gives you 3. Now so here what is happening? You are connecting only to 9 inputs, it is not fully connected, and that is what makes a difference. So there what was happening? You were connecting to all, but here what is happening? You are connecting to 9 inputs only, right? Now what is happening? So because of this, you are having fewer parameters. And then next what will happen? So you got this 3, now see your filter is moved, right? Filter is slide. Now again, what will happen here? This again, this multiplication will be performed with the corresponding term, and the response will be produced as -1. So again, you can connect it with the colors. So this 0 multiplied with 1, this 0 multiplied with this 1 multiplied with this one, like that, right? So this is your -1. Now what happens earlier? So it means what is happening? These image areas, the filter same, right? So what is happening here? We can say that this is an example of shared weights. So the same weights, the same filter, right? So earlier these pixels were getting this weight. Now you have moved the other pixels. They are also getting the same weight. So that is what is the example of shared weights. And because of shared weight, earlier you have saved it because saving was there because you are not doing this fully connected network, fewer parameters. Then because of weight sharing, even you are getting fewer parameters, right? So that is the benefit. Right? So with this, if you go to the complete generalized, you can say CNN architecture. So here you can see this is your picture. Now convolution layer, pooling layer, convolution layer, pooling layer, and in fact what happens as it is written, it can repeat many times. Right? And finally what will happen? Last layer here, that is your fully connected feed forward. Right? So you have flattened the data, and then finally the classification results are being generated. So here, convolution layer, now you are aware, so it is time to learn about pooling. Right? So pooling layer. Now because the image is large, as someone of you was correctly pointing out, image is large, so we need to accomplish the same for managing the input-output volume for the different convolution layer. So what happens here? We make use of pooling layers which make the representations smaller. And because of this, output volumes are more manageable. Right? See how. So here, remember that this pooling operates over each activation map independently. Right? So how it does work? Just see here. So this is your one slice, right? 224 cross 224 cross 64 is your volume and just one slice, right? So one activation map here. So here pooling, so basically what happens, we have performed this downsample, right? So you can see from 224 cross 224 to 112 cross 1. It means that you can see here the size is reduced to the length and breadth, they are reduced to half, right? So how to do this? So these are the common methods, this max pooling, min pooling, average pooling, and 79 slide. Yes. See what I am trying to say you here. Okay, let me read it once because this is important concept. Okay, I'm repeating. Okay. So you see here, so one thing you got that right now you are working. Okay, this thing you got. That you this input you will give like this, right? You have flattened it, so image is given like this, and at this point of time you are talking, you are connecting with only 9 inputs, right? Not all inputs which was there in the fully connected. So this point is clear. Now, what is the second point is the weight sharing. Because what happens, earlier your filter is this, now you have slided your filter. But the filter coefficients are same. So earlier these 9 pixels, they were sharing this weight. Now when you have moved, then again these are sharing the weights, the same weights. These weights are not different, right? So if when you are processing this image, you are going to process this entire image with this filter, right? So that is what we say that weight sharing. So weights are shared. I hope it is clear. So let me quickly come to, okay. So average pooling, min pooling. So I mean most of the time we are making use of max pooling. Now just try to look over, if time will be there, I will tell you why not average pooling. So first of all, again, let us say one example. We are taking this 2x2 filter with stripe. What is happening? So here you can see, so these 4, like the maximum ones, right? Simple concept. Again, if you are going to choose from here, the maximum. From here, if you want to choose the maximum. From here, right? So what happens here? Instead of these 4 pixels, only 1 pixel is coming, right? Instead of these 4 pixels, this is how the size is being reduced. This is how the downsampling is performed with the help of max pooling. So this is, you can see one example here. This is your input picture, and this is the result of max pooling. So here you can see this, right? So 2x2. That is usually like in the, if I remember correctly, LeNet or LXNet in one network, the max pooling was also taking the common this thing input, right? Like in the convolution we did, just one slide was there. But here you can see that we are doing this independently, right? So these 4 pixels, the maximum one, these 4 pixels, the maximum one, like that, right? So this is how from 6x6 you are getting this 3 pixels, right? Then average pooling, again this 4 pixels, they are being replaced by the average, right? So here you can see this -1, 2, 3 and -4 average. Get the average of this. So as you can see here, -5 plus 5 is 0. Again here it is 3 by 4. Again here it is -2 by 3, 4. Then here it is 4. Right? So this is average. Similarly, it is min pooling. Right? So you will take the minimum of this. Which is the minimum of this? -4, right? Again here -1. Here -2, here again minus, right? So now when we go for max pooling, then remember this is one example. So here these images are there, and again the 3 different images are being shown for this character 8, and this is the result of this max pooling. Now max pooling also performs as a noise suppressant. So it actually discards the noisy activations altogether. And it also performs the denoising, you can say, along with the dimensionality reduction. But if we take average pooling, then it simply performs dimension reduction as a noise suppressing mechanism. And therefore, we can say that the max pooling performs a lot better than the average pooling. So we'll find that most of the time this average, this max pooling is used. So pooling is what? Is a subsampling. And so see what we have done. So 4 pixels, we have taken the maximum one. So it is actually some type of subsampling. But what happens? We are not losing the image information. So if you just see this image, we are not using the image information. And at this point of time, what will happen? When your image is downsampled or subsampled, then fewer parameters will be needed to extract the features in order to recognize the pattern. Now, after this convolution, remember flattening, right? So after this convolution layer, pooling layer, then flattening was there, and then pooling. Flattening, what is happening? Simple, just arrange it in a 1D column, right? And so what remains here now? Fully connected layers. fully connected. So after this, you just pass it to fully connected feed-forward network as you do. So now this is your generic CNN architecture. Again, the same repeated here. So you can see here max pooling layer, convolution, max pooling, convolution, max pooling, many will be there. So at each stage, so that is why what I was showing you the activation maps. So after here you can get, so after every this thing, you will get a new image. Then, so this is an example of another convolutional network. Here you can see this bus. So here this classification is there between truck, car, among this aeroplane, ship, horse, and you can see here, this is how convolutional layer, this activation, right? Then pooling layer, you can see this pooling layer is interspersed, right? And finally, it is your fully connected. Right? So here we can see the filters which are being used here. The convolution filters are your 10 filters of 3x3, and stride is 1, padding is 1, and for pooling, generally this is your 2x2, as I gave you in the example, this 2x2, and stride is 2. Yes, some question is there? Abid, please write it on chat. Okay, so now with this, let us see the advantage of CNN in dealing the high dimensional data. Remember here, what is happening? The number of connections are reduced. So we are not having this fully connected, but the sparse interactions are there. So pooling, okay, you didn't get pooling, just a minute. See, let us first give me one example of pooling, then I will come to that. See, here pooling is simple, right? If you, let us say, just let me come to the features. So let first do this. So let us say here the pooling is there. So when you are doing this, when you are doing max, so here you have chosen that you are going to do the pooling into cross filters, right? So these 4 pixels were there, and then stride is 2. So you can see that these 4 pixels, then these 4 pixels, like that. Now in this group, if it is a min pooling, you will keep the minimum one. If it is a max pooling, you will keep the maximum one. If it is average pooling, then you will take the average of these 4. So this, instead of this 16, this 4x4, what will happen? We will get an image of 2x2, right? So that is 2. So let me complete it first, and then I will go to the padding. Otherwise, I will not be able to complete it, right? So I will take up those who are not getting, I will take up those questions at the end. Otherwise, the process is going to be, I wanted to explain with the process how the features are actually being right. So here this is being shown. So when you are saying that what is the difference between ReLU and pooling, see what is happening when you are using a filter. Let us say you are using some filter. So as a response, you are getting filter map. Now on that filter map, you are applying activation function. So like for example, let us say you are in the filter map, you are getting values just a minute, like this. Right, and so let us say this type of activation map you are getting. Now, when you are going to apply this ReLU activation function, what will ReLU will do? As I showed you, these non-negative values, these negative values, they will be mapped to 0. And this value, that will remain as it. So what will be there in the activation map? 3 will be as it is, -2 becomes 0, this -1 will become 0, like that. So here, as a response of convolution operation, you are getting filter map. Then you are applying activation function and you are getting this activation. Here ReLU means that you are using, there are many other activation function, here you are using ReLU, right? Now after these two things, then this convolutional layers now, and each convolutional layer, the details are given as per, right? Now after this you are doing this pooling. So as I have explained, So then again you have used here two convolutional layers, and after that pooling. So after two convolutional layers there is pooling, and at the final it is fully connected, right, which will give you the class. Okay. So this is so what is the advantage of CNN, which we discussed, and if you summarize it, so the number of connections are reduced, parameter sharing is there, then pooling layers actually are compressing the output volumes we just saw, right? Reduce the volume, and as madam explained you, so some type of transformations like translation. So if it is needed, this process needs to get invariant to that, right? So because of all these things, what happens? The number of parameters which we are supposed to learn becomes much less. So we just saw that comparison of the fully connected layer and convolution layer. Right? Another thing is that it allows you to work with input of variable size, whatever is included. Right? And but remember, this how it will work. That will all depend on how many filters you will use for training, and that is not so magic. So now let us come to this thing, how it actually works. So when we are talking about training a convolutional neural network, so what is happening here? You can say that first of all, you are having, let us say, this data. So you split and pre-process your data. So you need ground truth basically, right? For training, and that is why it is a very much time-consuming job, and getting a good data set for a particular application is very critical. So first of all, you need to pre-process, split and pre-process your data. Split means you will decide, okay, this much is for training, this much is for validation, this much is for testing. Then here, next step is that you need to choose your architecture there. And then you are going to initialize the weights. And after that, you are going to find the learning rate and regularization strength. Then finally, why we are doing this? We are doing this so that the loss may be minimized, and we need to process the we need to monitor the progress so that the loss may be minimized. And here, let me tell you, the many knobs are supposed to be figured out, right? For example, which network architecture? There are several architecture, right? So Google Net, RESTnet, mobile net, right? So I mean, so many. So which network architecture you are going to take? Then what will be your learning rate, decay schedule? What is the regularization you are going to use? Dropout or max normalization, so that this overfitting may be reduced. Because what happens? It may happen that you have trained your model. But that is an overfitted. Overfitted means that it is giving you good result for that particular set of data. But but it is not generalized. So when you are giving it a new data, then it will not give you the answer as it is expected. Right? So you need to do the regularization to reduce overfitting. Then which loss function you are going to use, because here you are supposed to minimize the loss, and then as I told you in the beginning, some weight initialization, right? So all those parameters are supposed to be fitted out. And then let me explain you this entire process so that the things will be very much clear to you, that how it is working, and finally how it is extracting the features. So here, if you see this overall process of training CNN, so first step, what we'll do, so here you can see that, let us say some images there, this is some both images there. And so first step is, number one, that we need to initialize, because in the beginning we don't know what are the weights of the those filters. So we need to initialize all filters and parameters. You can say we are going to initialize those filters with the random values. Okay. Now, what is the second step? Second step says that now your network will take this. Let us say this is your training image. Okay. So your network takes this training image as input, and it goes through forward propagation step, right? This is so forward propagation step, where you can see that convolution, ReLU, and then pooling, again convolution and ReLU, so pooling. So ReLU is given just an example here. Basically, ReLU is for some activation function you need to use, right? and then this finally this fully connected layer, right? So let us say when for this input, when you're with the after you have done the initialization and all, when this whole process completes, when you go to the end of this forward propagation step, then some probabilities it is your network is going to learn. So let us say the probabilities are okay. Let us say this is 0.2, 0.4, 0.1 and 0.3, right? Ideally what is happening, your boat, this is your boat image, right? So ideally you should get is 0 0 1 0, right? But because your network is not yet trained, right? So at the end of this forward propagation step, you are getting probability as 0.2, 0.4, 0.1 and 0.3. So you can see that actually it should be 1, but it is 0.1. So it is far from the reality, right? Because what is happening, as I told you, the weights are randomly assigned for this. This is your first training example, let us say. So the output probabilities are also random. Okay. Now the third step is what? Here. The third step is that calculate the total error at the output. Now here you can see that, like for example here, target should be 1, right, for both, but it is actually it is 0.1. So, but you will not do it for both only, because for all the classes, that is how this summation sign is, right? So you are going to calculate the total error at the output layer. So you can say that summation over all 4 classes in this particular example, right? So this is your third step. Now, what is your fourth step? Fourth step is your back propagation. So here also, how do you learn the filters? How do you learn the weights of the filter? Like you do it in the neural network. So using back propagation, right? So so now there will be back propagation, and there you are going to calculate the gradient of the error. I will not go into the nitty-gritty of that because we have already done that. So to calculate the gradient of the error with respect to all weights in the network, and then gradient descent will be used to update, let us say, all filter values or weights, and so that the error may be minimized, right? So here remember that what is happening, depending, here you are calculating the error, right? Sorry. And based on the error, the weights are updated, okay? So now what will happen? After back propagation, these weights are updated as per this error function, right? Now let us say you are giving the same image again as input. Then what will happen? The output probabilities will be updated. So now let us say output probabilities are 0.1, let us say 0.1, then 0.7 and 0.1. Now you can see that in the first go, your probabilities were 0.2, 0.4, 0.1 and 0.3, but now the probabilities are updated, right? Yes, any this thing you can do. So what is happening here? Now after this back propagation, so as you understood there, what is happening? The weights are being updated, and now you can see that your weight, now it is closer to what is there. You want it to be 1. Now after this it is 0.7. It means that now you are close to your target vector, because your target vector was 0 0 1 0. Okay, so this means that your network has learned something, right? So your network has learned to classify this particular image, and by adjusting the weights and you can say filter, so that the output error may be reduced, right? And here the parameters like number of filters, filter size, network architecture, they have all been fixed at step 1, right? You cannot change in these layers or these architecture in between. So you need to fix up everything at the step 1, and then you need to proceed. So in the training process, you are learning only the filter metrics, and the connection weights are going to be updated, right? And finally, what you will do, fifth step, final step in the training process, you are going to repeat all these steps, step number 1 to 4, for all the images in the trainings. And once it is done, you will say that now my convolutional neural network is trained. So what is the meaning of this? Your network is trained, that the weights and the parameters of your network have been optimized, and they are correctly classifying the images from the training set. And now when you will give an unseen image to this network, then this convolutional network, then this network will again go through the forward propagation step and will give you output. Now no back propagation. Okay, back propagation is there when learning. Now the weights are learned. So when you will give a test image, or you can say unseen image, the network would go through the forward propagation step and it will output a probability for each class, right? So for a new image, what will happen? The output probabilities are calculated using the weights which are already optimized during the training process, so that they were for classifying the training images. Okay, so if your training data set is large enough, then we can say that the network, like hopefully the network will generalize well to new images, and it will classify them to correct. Right? This is the final working with these components. Okay. So now next is I would like to tell you about some architecture. So is this up to this point? Is it clear? Okay, let us take up some question here.
Yes, please. Yeah. So let me request the participants. Now we have 7 minutes perhaps. So
no, actually I wanted to tell them about some architectures.
Okay.
But there are some
recent architecture you're talking about. Some deep learning architecture Dr. Santosh Viparthi is going to do. But if you wish to tell about certain architecture,
no, I have taken
you can.
basic things.
Okay, you please continue. Then maybe we can ask the participants at the end. If you don't, you can continue then. Yeah.
So there are several CNN architectures, as you can see here. The beginning one, as I told you in the beginning, that LXNet, then VGG, GoogleNet, RESTNet, I mean so many. So I would just like to tell you about a brief history of this, how these convolutional neural network came into the picture. So we know that like perceptron, when we talk about, then they were known long back. But what happened, I mean, the credit goes to like the beginning, right? So it lies with LeNet 5. So LeNet was one of the earliest convolutional neural network that was promoted to the basically deep learning. So what happens here? This Leacon, right, who is shown here, that is at the Bell Lab. He actually first applied back propagation. So as you can see there, how this learning is possible, not with the only feed forward, right? With the back propagation, the weights are being learned. So he first applied this back propagation algorithm to some practical application, and that is how it is being observed that the network can be generalized and for a particular task of a particular domain. So they first do it for the US Postal Service, so zip code of the US Postal Service. And here you can see that this architecture, so where you can see these convolutional layers, then this So I will quickly go through it because we don't have much time. So here you can see that there are 5 layers with learnable parameters. And if you guess how many parameters are there, then around 60,000 parameters over there. So here you can see this, the input to this network was a gray label image, right? 32 cross 32 into 1. So gray label image, then you can see here the first layer, convolutional layer, use 6 filters. Like you can connect it what we have just discussed, right? So 5 cross 5 filters and 6 filters, stride is 1 and activation function is this, right? So then they did this average pooling and again this convolutional layer and then like that, right? So now I hope you will be able to connect what we have discussed. So here, before just ending, I would like to tell you about this ImageNet large scale visual recognition challenge. And what happens here, I hope those who are working in the field of image vision, computer vision, they must be knowing this the Professor Feifei Lee. So basically, she was working on some medical image processing, and I mean, she was not able to work in the absence of the data. So what she did is that she decided to go for having a good data source which will serve for all the researchers. And I mean, as I heard in one of her TED talk, that at that time people understood that what is she doing, wasting her time, like, because it took a lot of time and with no output there. Because the initial papers, they collected the data set and they just published like how the papers on that data set. But later on, it proves a very fruitful resource for all the researchers. So the idea with the when she collected that data set was then this challenge was being launched in 2009, and here this visual data set contains now 15 million of labeled high resolution images of 22,000 category. It is having a hierarchical structure. So basically, at that time, there was a word net, and from the word net, the words are arranged in the hierarchical structure, and on that, she got this idea to to use it on the images, and so this has become a very very high quality data set. And then what happened, this challenge was being launched, which held in 2010, and since then since 2017 it is yearly held. And then every time, like, they use a small portion of the data set, let us say 1,000 categories for testing, and for training this 1.3 million, and this validation images, and these many testing sets. So the task, various tasks were given: image classification, object detection, object localization, and then what was the criteria to choose the winner? That is minimal, top 1, and top error rates. Now, what do you mean by top 5 error rates? Basically, when you are getting the similar image, right, like this, so the percentage or the labels, the top 5 labels, so the percentage of images where the correct labels is not one of the model's 5 most likely, right? So that is your error, top 5. So based on that, actually, this I was talking about this LXNet. So based on that, we get the major breakthrough in 2012, where this LXNet actually won this competition, right? So here, if we talk about LXNet, then it was a similar framework to Beacon gave earlier, but this was a bigger model. So it was having 7 hidden layers, and you can see, I mean, how many parameters. And at that time, why I wanted to mention it, because you must understand, at that time we were not having that much computational facility available. So they need this GPU implementation. So what is being done? It is trained on 2 GPUs, right? So they use GPU that was 50 times speed up, but still, like, the whole thing cannot be done on one system. So they trained it on 2 GPUs, right? So here, this is how. So this is your LXNet, which is processing on image. So you can see that each layer, right? Each in the hierarchy, we are learning the higher order. You can say from lines, from edges to objects. So I'm sorry, I'm taking it a bit quickly. So here you can see this 8 layers are there, and in fact, this has popularized reduction function, and multiple GPUs, or you can see these parameters, 62.3 million parameters. So therefore, there was quite a chance for overfitting, and because of that, this heavy data augmentation and dropouts are being used to avoid it. Right? And here again, now here I was telling you, like the pooling which I told you, their overlapping was not. You are choosing 2 cross 2 is strike 2, so that the next bunch you are choosing. But in LXNet, they used overlap. So this is again, you can just so you can see here 11 cross 11, then 3 cross 3, 5 cross 5. Like so, because there is not much time, so I will just. So here, just see this. The network, as I showed you, the network was split across 2 GPUs. And that is how you can see the split in the architecture. So when you will see these pictures, because they are trained on a different GPUs, so that is how. So these were the result of LXNet, and this is your, you can say this classification. So that is how this LXNet gave you the first point. This was the first CNN-based winner. As I told you, 85% accuracy as compared to others. So, but now we have, reaching quite far from there. So you can say from 8 layers to Google Net is ResNet is 152 layers. So not way we have gone. So this is your VGG. Now, just let me tell you what is the difference between the VGG and LXNet. Basically, there are so LXNet, that is the basic. One. So now, nowadays architecture, as Madam told you that so Dr. Tripathi will take up. So nowadays we have reached far ahead. So, but if you just summarize here with VGGs, what happens that if you remember this LXNet, they use this 11 cross 11. So, right, somebody was asking about the size also. So instead of using this 11 cross 11 filters, right, with a stride of 4, there, this VGG uses small filters, so 3 cross 3 with a stride of 1. Now, because what is happening, there are 3 ReLU units instead of just 1. So decision function becomes more descriptive. Right. So what they did is they added number of layers, but they reduces the size of the filter. So here you can see that this is your network, and so what is the total number of parameter here? So it's 138. So now here I would like to mention one interesting fact. Now at the Google, when in their lab, they built a neural network with 16,000 computer processors and 1 billion connection, and they allowed it to browse the YouTube. Then what happens here? You can see that this network has started looking for cat. Right. So this is I thought, although it is long back news, but I thought it might be interesting. So because everything requires interesting deployment, and because of this usefulness, nowadays neural networks, CNNs, that are being used everywhere. So you can see Facebook, Google, Microsoft, and it is not only used in this area, image like speech, and other areas are also there. And the important point here is to understand that although it takes more time in training, but the things become fast at the test. So that is all from my side here. So these are the references. These are the very good courses, and I would like to thank Professor Oja, because most of the slides I have taken from her.
Oh, you have, in fact, you have enriched those slides, Preeti. Those are very skeleton slides. Thank you so very much. And
these are all legendary. You go through the course from FEPLE, from this CMU course. I like this very much. So please go through these courses and learn more. So, yeah.
Very nice.
Now we will take finally some more questions. I'm sorry I'm 5 minutes out of time.
Thank you so very much, Professor Khanna, and I always like to call you Preeti, although, but this was such an awesome session. I'm sure that participants have been benefited by your wonderful exposition. May I request participants, if you have any questions, please, you can raise your hand, and then we'll have. I'll take some short 3 questions. Please raise your hands if you have any questions. So there is a question. There is a Vidushi Singh, who is my very old, very bright student. Vidushi, she is writing, thanks a lot, madam, for wonderful session. Yes, I also thank Professor Khanna, because she relieved me today. It was supposed to be my session, but then she very kindly accepted our invitation. Any other question you have in your mind? So, because she has already addressed your basic questions, and she has explained so very well, I am sure that So There are no more questions, it seems. Okay.
Thank you so much. Thank you so much for patient hearing and asking questions. So, in case you have any
Recording
query,
stopped.
we are here only. So, I mean, you can even even pass on your queries if any. So, you just go through this, and even if there is anything not clear, you can pass it on. I will be happy.
Thank you so very much. And we will share the PPT soon because she is with me. I'm sure that she is going to immediately share this. Participants, on behalf of participants, and in fact, on behalf of all the coordinators of EICT academies at IIT Roorkee, again, it's my pleasant duty to convey our sincere thanks to you. IIT Roorkee, MNIT Jaipur, NIT Patna, NIT Warangal, and IIIT DM Jabalpur. We sincerely thank you, Preeti.
Thank you,
ma'am. And it was wonderful, such a wonderful session.
It's always a pleasure working with you, and thank you so much.
I've learned a lot from you. Thank you so much, and thanks participants for your active involvement. We are going to meet at 6 p.m. Purnima is going to cover to help you with building your own CNN model, classification model. And so 6 p.m. Before 6 p.m., I request you all to please join. Thank you. So I'm ending the session for all. Thank you once again, Preeti. Bye.